then compute the R. Okay, always do a picture first. We've been stressing that the entire course. So we've already done one of these, right? In the past, we looked at the picture of this. So a study was done, conducted to determine if the amount a person spends per month on recreation is related to the person's income. Determine the correlation coefficient R and comment on their relationship. So before we just did a scatter plot. So hopefully I still have that data in here. Let's pull up the TI. And there it is, right? So if you've already cleared that out for some reason, stat edit, put that data in. We always look at a picture first. We look at the graph. There we go. So it just does look like it's sort of trending upward, right? We want to find the correlation coefficient. So let's go ahead and press stat. Scroll over to calc. We want to calculate something. Oh, before we do this, well, let me do this first and see what happens. Linear regression. And you can just press enter. I typically will go ahead and put L1, comma, L2, and press enter. Now that will oftentimes give it to me, but watch this right here. I don't have the R. I should have a nice R there, and I don't have it. So what happened? And I'm glad this happened this way, because you will most likely have to turn this on. And I wish it were turned on by default, but it's not. So to turn the diagnostic on, you're going to press second and catalog. I believe is the only place it is. And it starts with a D. Notice alpha is already selected, so I can press the D, which is this button here, X to the -1. We'll scroll down to D, or you can just scroll down there. I just didn't feel like waiting. And diagnostic on. The little triangles right there. Press enter, and then press enter. Now let me repeat what I just did. Stat, calc, number 4, and then L1, comma, L2. And press enter. Now notice what it gives me. It gives me two other values. For now we're just going to talk about R. And so R is about 0.9. So this would be a very strong, right? A strong positive correlation. And I guess we could put the adjective very in there, very strong. Or I guess that's an adverb, right? So a very strong positive correlation between these two, the income and the amount spent on recreation. Okay, let's look at this one. Does how long children remain at the lunch table help predict how much they eat? The table gives data on 20 toddlers observed over several months at a nursery school. Time is the average number of minutes a child spent at the table when lunch was served. And calories is the average number of calories the child consumed during lunch, calculated by careful observation of what the child actually ate each day. Okay, so here's my data. What's the first thing you're going to do with this? Oh, by the way, let me go ahead and put the questions. We're going to find the correlation coefficient for the data, write a sentence or two explaining what it means, and then we're going to comment on this analyst's conclusion, see what it, if you think it's an appropriate conclusion or not. Let's go back to the data. Now we want to go ahead and crunch this out into a picture, right? That's the first thing we always do with this data. We want to look at a picture of the data. I mean, can we even calculate a correlation coefficient for this? Because we're only looking at linear data, right? That's all we're going to look at in here. Okay, now I've already shown you how to do one in the TI. Now you can certainly do that on the TI, but the you got to first determine which one is the X and which one's the Y, right? So which one is the explanatory variable, which one's the response variable? Think about it for a second. So time is going to be X, right? That's the explanatory variable. Does time explain the response, which is the number of calories? Okay, so again, we usually let time be L1, or X be L1, and Y be L2. So be careful on that. Okay, I'm going to show you how to do this in StatCrunch. And really, any software package would be very similar. So in StatCrunch, we are going to put the data in, and then go over here to Stat, Regression. Simple linear regression is what this is called. X variable, that's when we pick time. Y variable, calories. Click next. We're not going to worry about this now. Click next. We're not going to worry about any of that. These are all the default options. We're not going to worry about any of that. We may in the next section. Click next and calculate. Looks like a lot of stuff, but really the only thing we're looking at is R. We wanted to find R. There's R. Negative 0.6492. So what does that tell me? R of negative 0.6492. Negative 0.6492. So I would say that's a moderately negative relationship, right? Moderate negative. So what we got here? So write a sentence or two explaining what this correlation means for these data. Remember to write about the food consumption by toddlers rather than about the correlation coefficients itself. So you don't want to just say there's a moderate negative correlation. That's the first thing we say, but then we want to attach it to the context of the problem. And this is really key. Make sure that you're able to do this. And then I'll let you do that on your own, and we'll come back to it in a second. And then part C, one analyst concluded, it is clear from this correlation that toddlers who spend more time at the table eat less. Evidently something about being at the table causes them to lose their appetites. Explain why this explanation is not an appropriate conclusion from what we know about the data. So pause the video here, and on the next slide I'll reveal the answer. But really try to think about it. Try to form your own words, particularly for B. Okay, welcome back. So we've already mentioned this 0.649 or moderate negative correlation. So here's the sentence. Toddlers who spend more time at the table tended to consume fewer calories. It doesn't cause them to do this. And this is where the analyst actually made a mistake, right? It's completely speculative. There are lots of possible explanations for the behavior of toddlers. It just shows us an association between these, not the same as cause and effect. Which is a good intro into our, I think is the last little mini section here. Correlation is not causation. So here's an example. Strong positive linear relationship between children reading skills with shoe size. So we got shoe size on the explanatory axis, reading index on the response. So if we make children's feet grow faster, they'll become better readers? No. We need to watch for lurking variables. So there's a variable, an underlying variable here that's really explaining why the reading index goes up. It's probably age in this case. Kids that are older typically have bigger shoe sizes, and people who are older are usually better readers. So this is an example that correlation is not causation. So again, a lurking variable is just, it's a variable related to both the explanatory variable and the response variable. And we'll see several examples of this. Here's another one. A survey of the world's nations in 2004 shows a strong positive correlation between percentage of country of the country using cell phones and life expectancy in years at birth. So does this mean that cell phones are good for your health? That is, do cell phones actually cause one to live longer? Well, no. It simply means that countries where cell phone use is high, the life expectancy tends to be high as well. So what might explain the strong correlation? Pause it and think about it for a minute. Most of these you can kind of come up with one or two things, right? So general economic conditions could affect both cell use and life expectancy. So countries that have more money generally have more cell phone use, better health care. So the economy here was a lurking variable.